All right, so we worked with function transformations quite a bit in Algebra 2, but they're coming back in pre-calc here. So let's just start by reading what we've got to begin. If a new function is formed by performing certain operations on a given function f, then the graph of the new function is called a transformation of the graph of f. The simplest function of its kind is a term you've seen, but we refer to it as a parent function. All other functions are transformations on the parent. So what we have here below are some examples of some parent functions. So I'm going to talk through briefly what different types of transformations would look like and kind of what our possibilities are. So our parent function for a linear function is just f of x equals a times x. Any sort of transformation we put on that. For linear functions, we can have f of x equals ax plus k. So what this means is we can have multipliers on x and we can add or subtract things. That's the only real things that can really happen with linear functions in terms of transformations. And we'll reference what these a and k mean, as well as some other letters. For absolute value functions, we can have a multiplier of a. We can add or subtract something on the inside of our absolute value and add or subtract something to the outside. So these are three different types of transformations that can possibly occur. And this is generally going to be the case for most of our functions. So like for a quadratic function, f of x equals x squared, we can have functional transformations of multipliers. We can add or subtract things on the inside, and we can add something to the end. And the location and notation in terms of like positive, negative for h, k, and a will definitely come in handy later on. Similarly, we can have a multiplier on a on our root function, square root function, our radical, as well as we can subtract something on the inside and add things on the outside. So you'll see this trend of being able to add things on the inside and outside, and they'll refer to different types of shifts. For cubic functions, very similar to our quadratic functions. For our exponential functions, we can again have a multiplier. For an exponential function, there really isn't like a parent function in terms of this number. We usually just think about it as b to the power of x, so any number to the power of x. And again, we can add or subtract kind of with the x. And lastly, with our logarithmic functions, and oops, this isn't a log function. Log functions extend forever, like so. So pretty similar, but a times log of x minus h plus k. Okay, so we have a few different letters happening here. So we have a, h, and k that have shown up in all of these. Well, except for linear, there's no h. In terms of vertical shifts, our k represents our vertical shift. In the sense where if it's positive, means we shift up. If it's negative, that means we shift down. Our horizontal shift, that refers to h, where if our h value is positive, we are shifting to the right, and if it's negative, we are shifting to the left. But keep in mind here, the form for all of these is x minus h, so if it's x minus 2, that h value of 2 would be positive because the form is minus, where if it's plus on the inside. So we should note x minus some value, so like x minus 2 would give us a shift to the right, whereas x plus 2 would give us a shift to the left. For stretches and compresses, that would be our a value. If a is greater than 1, we have a vertical stretch. If a is between 0 and 1, we have a vertical compression, or sometimes you'll see that written as a shrink. And lastly, reflections are whenever you have a negative a value. So these are our main types of transformations: vertical and horizontal shifts, stretches and compressions, and reflections, all of which you've seen before in different units in Algebra 2. So let's start just by performing some of these, looking at how some of these play out. So we'll start with just graphing vertical shifts. So when we graph our vertical shifts, and really when you're graphing any transformation, sometimes it can be helpful to just graph the parent function first and then go from there. So to begin, we have f of x equals x, or absolute value of x, or y equals the absolute value of x. So when we're plotting this function, I've actually just filled in the table for you, given you some values. So we'd have a point at negative 5, 5, a point at negative 3, 3, negative 1, 1, 0, 0, and then that ends up just being mirrored on the right side. So for our f of x function, remember absolute value, just kind of two straight lines going out, so this represents f of x. Vertical shifts occur when you're adding or subtracting things on the outside. So there are two ways you can plot these. One, you can just plug in values and get them that way and plot them accordingly. Or we can use the parent function to graph our shift. So if it's a vertical shift if we're adding 2 to the outside, this means we are shifting up by 2. So every single point here would shift up by 2. So I'm just taking all these points from the parent function and shifting them up by 2. And that'll give me g of x. For h of x, we have the absolute value of x minus 3. So this would give us a shift down 3. So we take our parent function, we go down 1, 2, 3, and we do the same for each of these values. So all these points that I plotted for my parent function, I'm just plotting new points 3 below for my new function, which is called h of x. So I'll just put h of x next to it so I can write. If you want to write in different colors, I suppose that's an option too. So vertical shifts, you just take the parent function, add or subtract whatever values those are. It does require you to have knowledge and be able to graph the parent function, of course. Okay. Example 2, horizontal shifts. So again, we want to start just by plotting our parent function. So to plot our parent function, you just plug in x values, figure out what your f of x or your y values are. So if we plug in negative 3 here, negative 3 squared is 9. Plug in negative 2, negative 2 squared is 4. Negative 1, negative 1 squared is 1. And so on. So you can go ahead and graph those, get those points, and now let's plot our quadratic function. So negative 3, 9, negative 2, 4, negative 1, 1, and 0, 0. And then we have 1, 1, 2, 4, 3, 9. Okay. There we go. So here we have f of x. Now we have two different other functions that are happening with some shifts. So we are subtracting 2 on the inside. So remember, whenever you see subtraction on the inside, that refers to a positive h value, meaning you should shift to the right. So x minus 2 here means we are shifting right by 2. So I'm going to take each of these points and just shift them to the right by 2. Again, there are other ways you can graph these, one of which being you can just plug things in and get points that way as well, but this works too. Next, we are adding 3 over here, so that would be a shift to the left by 3. These horizontal shifts are hardest to figure out just because it's kind of opposite from what you would think. So you'd think a negative would mean left and positive would mean right. Not the case. X minus 2 gives us a shift to the right. X plus 3 gives us a shift to the left. And notice these values are inside of parentheses. They're attached to x, which is how we know it's a horizontal shift as opposed to a vertical shift where they're on the outside. So we shift 3 to the left of our parent function here. A little hard to keep track here with all these lines happening. There we go. Okay, and there we have it. There is h of x. Okay. If you have a case where you're combining horizontal and vertical shifts, those are things you can perform together. So let's try that as well. So in this case, we have an example. We have g of x equals the square root of x plus 2 minus 3. So let's start by just graphing our parent function, the square root of x. So let's get some points. So we plug in -2 for x. That doesn't work. You can't take the square root of a negative because it'll be imaginary. Same with -1. But 0 will work. The square root of 0 is 0. Square root of 1 is 1. Square root of 2, well, is root 2, which is roughly 1.4. So then when we're going ahead, we graph this. We start at 0, 0, as radical functions do. We have a point at 1. We have a point at 2, 1.4. I know other square roots or perfect squares will apply. The square root of 4 will give us 2. 9 will give us 3. So we can plot some more points that way. Okay. So we've got our square root function. We have f of x. Now, g of x. Couple ways we can do this. One way you can do it is just by looking at what's happening here. So on the inside here, we're adding 2. So that's going to be to the left by 2. On the outside, we're subtracting 3. So that's going to be down 3. So what I can do is I can take all of these points and shift them to the left 2 and down 3. So left 2, down 3. Left 2, down 3. Left 2, down 3. Left 2, down 3, and left 2, down 3. We're right there. Okay. And now there we go. There's g of x. So it looks very similar. It looks like the same, just shifted to the left and down 3. Otherwise, you can always just plug in points, and that would work as well. So if we plug in -2 here, we get 0 minus 3, which is just -3. So -2, -3 is what we have. We plug in -1, we get the square root of 1, which is 1. Minus 3 is -2. Plug in 0, we get root 2 minus 3, which is what we have. You plug in 1, you get root 3 minus 3. You plug in 2, you get 4. Root 4 minus 3, or 2 minus 3, which is -1. So we have a point at 2, -1, which matches up as well. So whenever you're graphing these, you can always just plug things in, plot some points, or it can be pretty helpful just doing performing those transformations visually. So starting with the parent, then performing transformations. Okay. All right, the next piece here is a reflection. So again, let's start just by graphing our parent absolute value function. So we can fill in these values here, knowing the absolute value just makes everything positive. Okay, there we go, we've got f of x. Okay, when we are graphing transformations, there's a kind of proper order, I would say, to go about these. So when you are graphing these, you want to be very, very careful. So you'll want to start here by thinking first in terms of a reflection. So let's call g of x negative. absolute value of x. So if we think in terms of the reflection first, it's basically the same values, but we're just changing their sign to negative because that negative's on the outside. So this is a reflection over the x-axis. So basically every point just gets flipped straight over the x-axis. So it's a mirror image over the x. So when we're graphing here, we'll call it, that'll be our g of x, so negative. From there, we have a shift to the right 2 and up 3, so then you would take every point and shift it to the right 2 and up 3. So it's going to look more so like this. Okay. And that'll be our y equals negative x plus 2 plus 3. So the rule kind of here first is first you do reflections, then you do shifts. Okay. The last thing we have, the thing we've yet to talk about here, are stretches and compressions. So with stretches and compressions, these ones can be a little tricky. So again, we're working with the absolute value function. So let's start just by plotting that. And what we'll want to do here is, well, there's a couple ways to think about it. One, you can always just plug things in and graph. But it's nice to be able to do things at least kind of visually. And what I recommend doing first is applying that stretch first. So it is a stretch since that 2 is larger than 1. And what that stretch will do is, well, it's just going to multiply all your y values, or f of x values, by 2. So it's just going to multiply everything by 2. So 1 times 2 is 2, 2 times 2 is 4, 3 times 4 is 6, 4 times 4 is 8. And the same would apply here. Basically, it looks like 2 linear functions with slopes of 2 and negative 2, or negative 1/2 and 2. Or wait, yeah, negative 2 and 2. So we'll call that our g of x. And then you can perform your vertical or horizontal shift. So here we have right 2, up 3. So we just take all these points, shift them to the right 2 and up 3. Right 2 and up 3. Right 2 and up 3. And the same would apply with your other points. So that there would be our y. So in this case, what we did was we did our stretch, or if we had a compression, we would do that. We did our stretch first, and then we performed those shifts. And that's generally, that is how you're going to want to go about this. So there are situations where doing the shifts would work first, but generally speaking, the way that you always want to start with these is start by doing your compressions or compression/shrink or stretches, then your reflections, then your shifts. And that'll just ensure you're not making any mistakes. Like I said, there are some situations where doing it out of order will still work for you, but doing it in this order will always make sure you're graphing correctly. And what's nice is we have calculators, so you can always check, plot your function on your calculator, make sure everything checks out, and you're all set.